All right, let's dive into one of the most important experiments in your entire GCSE chemistry course, making a pure, dry salt sample. Now, this isn't just about splashing some chemicals together, it's all about precision and purity. Honestly, if you can nail this practical, you're on your way to banking some serious marks in your exam. So let's get right into it.
So here's the plan. We'll start with the goal, what we're actually trying to make. Then we'll walk through the method, step by step, and of course cover the essential safety stuff. But then we get to the really important bit, the exam thinking. We're going to break down exactly why we do each step, because that's the secret to unlocking those top-tier marks. Let's get started.
So, first things first, what's actually happening inside that beaker? Well, at its heart, this whole practical is built on one of the most fundamental ideas in chemistry, a classic neutralization reaction.
This simple word equation right here, it's basically the blueprint for everything we're about to do. We take an acid, we react it with a base that doesn't dissolve in water, something like copper oxide. And what do we get? Two things, our target soluble salt and a little bit of water. It's simple, it's elegant, and it's the key to the whole process.
And here's the really cool part. You can actually predict the exact salt you're going to make just by looking at the ingredients. Check out this table. The first part of the salt's name, you see, always comes from the metal in the base. So, copper, zinc, magnesium. The second part, that comes from the acid. Sulfuric acid always makes a sulfate. Hydrochloric acid makes a chloride. You see the pattern? It works every single time.
Right, let's get into the method itself. Like I said, this isn't just a case of mixing two things together. It's a very precise, multi-stage process, and it's all designed to create a really pure product.
Okay, so it all breaks down into 5 key stages, and each one gets us a step closer to those pure salt crystals. We warm, we add, we filter, we evaporate, and finally, we crystallize. So let's break down each of those steps, starting with warming the acid.
Step 1, we gently warm our dilute acid. And notice I'm saying gently. We are not trying to boil it. All we're doing is giving the acid particles a little energy boost. By increasing their kinetic energy, they start moving faster, which means you get more frequent, more energetic collisions with the base. And what does that mean? Well, it just speeds the whole reaction up.
Next up, we start adding our insoluble base. And the really crucial part here is that we add it in excess. That means we keep adding it and stirring until we can actually see a layer of unreacted solid just sitting at the bottom of the beaker. That's our signal. That's how we know for sure that all the acid has been used up.
So, how do we get rid of that leftover solid? Easy. We filter it. We just pour the mixture through some filter paper, all that unreacted base gets caught in the paper, and here's a key word for you. We call this the residue. The beautiful clear liquid that passes through, that contains our dissolved salt. That's our prize, and it's called the filtrate. Now we take our filtrate, pour it into an evaporating basin, and again, we gently heat it. The goal here isn't to boil it all away, but just to evaporate about half of the water. This creates a really concentrated, saturated solution. A little pro tip to check if it's ready: dip a glass rod in. If crystals form on the rod as it cools, you're good to go.
And for the grand finale, we just turn off the heat and leave our saturated solution to cool down nice and slowly. As that temperature drops, the salt becomes less soluble, and you'll see these beautiful, pure crystals start to form. All that's left to do then is to pat them dry with some filter paper, and you're done.
Okay, so we've got the method down. But in any practical, safety and knowing what to look for are just as important. So let's quickly cover the essentials. Right, these are absolutely non-negotiable. Goggles on at all times, okay? We're working with acid and heat. You need to be standing up, not sitting down, so you can move away quickly if there's a spill. And of course, just remember that the beaker and evaporating basin are going to be hot.
So how do you know when to stop adding that base back in step 2? Well, your key observation is this. The solid base will literally stop dissolving. It'll just sink to the bottom. And if you happen to use a carbonate as your base, any fizzing will also have stopped. That is your green light. It tells you all the acid has been neutralized.
Now, this next section, this is where the top marks are won in an exam. It's not enough to just know the method, you have to be able to explain why each step is so important. So let's get into some proper exam-style thinking.
First up, here's a question you will almost certainly see pop up on an exam paper. Why on earth do we deliberately add the base in excess? What's the point of adding more than we need, only to filter it off again later?
The answer is actually really simple and precise. We do it to make absolutely sure that all of the acid is completely used up. Think about it. If any acid was left over, our final salt sample wouldn't be pure, would it?
It'd be contaminated with unreacted acid.
Okay, next question. What's the specific reason for that filtration step? Why can't we just skip it and go straight to evaporating after we've added the base?
Well, the reasoning follows on perfectly from the last point. We filter specifically to get rid of the excess solid base that we added. Since the base is insoluble, but our salt is soluble, filtration is the perfect way to separate them. It leaves us with a pure solution of just our salt and water.
And finally, a big one. This is a very common mistake that students make. Why do we just gently evaporate some of the water and then let it cool instead of just whacking the heat up and boiling it all away until it's completely dry?
There are two absolutely crucial reasons for this. First, slow and gentle cooling is what allows those large, well-defined crystals to form. If you just boil it dry, you just end up with a useless powder. But maybe even more importantly, many salts, like copper sulfate, are what we call hydrated. This just means that water molecules are actually part of their crystal structure. If you heat them too strongly, you drive that water off, which literally breaks the crystals down and destroys your product.
All right, let's wrap this up by summarizing the absolute must-know points. You can think of this as the perfect structure for a high-scoring 6-mark exam answer.
Just burn these 3 justifications into your brain. 1, you add the base in excess to make sure all the acid is neutralized. 2, you filter to remove that excess solid to get a pure solution. And 3, you crystallize slowly to get large, pure crystals. If you can nail these 3 points, you are well on your way to full marks.
So, the big question is, are you ready to describe and explain this method for a full 6 marks? I think you are. You've seen the what, you've seen the how, and most importantly, you now know the why. You've got the method, the safety, and the scientific thinking to back it all up. You can go into that exam with confidence. You've totally got this.